Hey guys, welcome back. Alright, if you're just now joining us, we're in the middle of working through an ordinary least squares regression example. I'll put a link down to the first video in the comment section below. But this is a data set located in the carData package within R that examines salary outcomes for college professors, given a whole bunch of other variables during the academic year 2008 and 2009. So I've just reopened the R Markdown file that we're kind of working out of, and I can see a couple things that I need to change. First off, I'm going to change the new date. It's been a couple days since I recorded the first video, so I'll update that. And then I'm also going to want to add a new library to the initial chunk that kind of specifies the library or packages that we need. And I'm going to put in library R MISC for miscellaneous. So if you don't have this library, you're going to want to download that. Use the install.packages command in order to download this, or you can go over here within the packages tab. You can click that install button and you can search for whatever package you need, and it'll give you exactly what you're going for. All right, so great. So once we have that, then we're ready to kind of scroll down. So before we downloaded our data, we actually examined the first few observations, and we noticed that we have both the rank of the professors, whether it's assistant, associate, or full professor. Discipline is a binary indicator, I believe. If it's A, takes the value of A if it's in a theoretical discipline, and B if it's in an applied discipline. We have the number of years since that professor attained their PhD, the number of years they were in service to that particular industry. We have a binary gender categorical variable for capturing either male or female, and then we actually have the salary information here. Now I've previewed the this head command within the R Markdown environment, and you can see something that's I should at least bring to your attention here. Notice below rank, discipline, and sex, you'll see this little factor. I'll highlight it there. Hopefully you can still see it within the screen, but you'll see like this within this little bracket. You'll see factor. That kind of specifies the class of data that variable is. At one point, I'm going to do a video on the various data classes within R. But this is going to mean something to us when we actually do run our linear regression here in a few minutes. So just going to keep that in the back of your head. We're going to come back to that. We'll see that salary, of course, right underneath that salary button is integer, as well as for years since PhD and the years of service within that university. All right, we plotted some data and kind of examined along the x-axis the years since PhD attainment, and on the y-axis we saw the salary and natural logarithms. Now this actually, I'm seeing I never actually closed my parentheses. Excuse me. Much better. All right, then let me rerun that. Also, something I should mention here: if you see this little this first middle icon here within an R code chunk, you'll see if you just put your cursor over top of it, it'll give you the preview. Run all chunks above this line so you can execute that, and it'll actually run these things and keep them now within your global environment. And then of course the button right beside it actually runs the current chunk. So I'll run the current chunk and then update. Yeah, there we go. All right, so we see we have a scatter plot here. And the Scatterplot kind of gives us some interesting information about the actual salary distributions among the disciplines and also the years of service based on the size of the dots. We can see that the longer you move away from your actual graduate school days, the higher your salary is likely to be, up to a point, and then it appears to have this kind of downward trajectory. So we clearly have some type of quadratic term here that we're going to want to eventually account for within our linear regression framework. We did some box plots, and yeah, so great. I won't go over all that. Like I said, you can go over everything that we said in the previous video. Now, okay, so let's actually examine our econometric model. So we'll put a new header down here, and I'll say econometric model. Now, an econometric model is going to be the actual specification of how we take the data and actually formalize it into an actual mathematical function here. So we're going to insert a math environment here. I'm going to put $2 signs. I'm going to enter a couple lines, and I'm going to put 2 more here. So notice this kind of gives us a highlighted area here, and in between those double dollar signs, we can actually specify the math type that will kind of specially format our math equation. Now this, within our Markdown, this is kind of a combination of both the LaTeX programming, which is a markup language for research. Usually this is used the most within academia, but of course it does have some applications outside. Very popular over in Europe, given that they don't like proprietary data all that or proprietary programs all that much. Here in the US it's a little bit, it's not quite as popular, although I love it. So we want, for our dependent variable, we want the log of salary. And that's going to be the variable that we're actually trying to explain, given everything else. And so the first term that we're going to have is going to be our intercept, beta 0. Now, inside of this, I should at least note here, whenever you have a Greek letter, put a slash before you spell it out. That'll actually that'll actually produce the glyph for that if I do that. Otherwise, it'll just specify beta down here. The other thing is the curly braces. Because this is a hybrid of Markdown, you could actually just do, if you have one character, you could omit the curly braces, but if you have more than one character inside of your subscript, you want to put it inside curly braces. Inside curly braces is standard LaTeX, so I'm going to probably use that just to kind of make life easy. And so I don't have to keep typing out beta. I'm going to copy that. Change that to beta 1. And for our first variable, our first independent variable, we'll put rank. And this is going to be individual I. And actually I should over here put individual I as well. All right. And then for beta 2, we'll want to use year since PhD, and I'll just put PhD as my variable. For beta 3, we'll put service, which will be the years of service. For beta 4, excuse me, we will put discipline. And then for, or was that, yeah, beta 5, yeah. Beta 5 we'll put our gender. And then we're also going to have an error term, and I'll just denote our error term with E. And now I'm going to go back and I'm going to add all of my I subscripts. I'll just copy them from the first, and then keep adding them to my actual variables. Great. Now, because my screen is relatively large here, this kind of, it's cut off a little bit in the preview mode here. If we actually go ahead and knit this out, this will be a little bit nicer. So let me knit that, and then we can see down below, it's at the very bottom unfortunately here, but you can see, okay, we actually have a nicely formatted math type equation. Notice that the words are all kind of italicized. We actually have math characters here, so we actually have the betas nicely formatted as well. So this gives us a full indication of the model that we're going to run, just given the variables that we have. And by default here, I'm going to call this model 1, if you will. I'm just going to throw everything at this. So I'll put all of the variables that we actually have in this data frame in order to explain our natural log of salary. So the next thing we need to do is we actually need to estimate that. Once we've actually taken our theoretical framework, now we need to convert this theoretical equation into an actual regression and run that within R. So we'll say estimation. I'll insert an R chunk here, and because this is our first pass, I'll just call this first model for lack of creativity. And then we'll use the function lm for linear model. And so you can see once you type in lm with an R markdown, it gives you a kind of a little preview box of all the various things that you might possibly want to put in here. We don't need nearly these many arguments filled in. Most of them are filled in by default here, but we do need to specify the formula. We do need to specify the data set in this case. So for our dependent variable, we're going to nest inside of this the mathematical function of log for salary. And you have to be careful here. You have to specify the actual name of the column within your data frame. So if you don't remember what that is, you may need to reload that and look at it to make sure that you actually capture the appropriate name. Because if you don't get this portion of it right, then it'll give an error message. The equal sign is given by the tilde. This is usually located below the escape key, but that kind of represents our equal sign. We have to be very careful in a relational programming language like R. This little arrow that we generate to kind of pipe our results directly into another object. This could also be just as easily substituted with an equal sign itself. So in order to get around that, a lot of the statistical packages, where you have to specify an actual function, they use a tilde to kind of represent what an equal sign should be. We'll put rank, we'll put years since PhD, I believe that is the actual spelling of that. We also have years of service. We have discipline. And we have sex. I think they called that gender variable sex rather than gender. And then we want to specify our data equal to our salaries data set. So by specifying the data set as an actual data frame, you can specify the name of the data frame, and then within that data frame, it's going to automatically specify or look for these variables within that data frame, or look for those specific columns within the data frame. Alright, so once we have that ready to go, then the very next thing I want to do is I want to use the summary function. And actually before that, let me actually specify, just have it print the actual model itself, just so you can see why we're going to use the summary function. So we really have three lines here. We have the first one kind of estimating our linear model and saving that as this object first model. Then I'm in line 68, I'm basically saying print this object first model, and then I want you to give me the summary of a first model. So let's run that. And we see kind of everything generated here, ready to go. Now, yeah. So the first thing in line 68, I said just give me print the model first model. And this is what it will generate for you. It'll generate first the call function. The call function is basically just a reiteration of exactly what you've told R to estimate. Now, usually whenever you're doing like just a one-off model real quick, or a single estimation, this is kind of redundant because I'm like, well, I know exactly what I just put in here. This is exceedingly helpful when you're running many different models and you're kind of going back after the fact and looking at the estimations. This becomes an invaluable tool. So, but when you're just doing one, you kind of feel like, okay, this reporting of the call function is not necessarily that helpful, but it is a nice summary, if you will, of exactly what it is you estimated. Notice here that we have just the coefficient estimates hanging out here according to each of the individual variable names of our independent variables in this model. This is all that you'll be given from when you actually print the first model. So this is why my default is automatically, whenever you estimate a model, use the summary function, because this doesn't give you very much information here. It's the summary function that actually gives you relatively more. So I'm actually going to go here now and delete that from our document here. I've included it for the sake of completeness, but let's now move on. All right, so now this is what we're left here with is the full summary of this, and I'm going to maximize this little window a little bit. Again, it prints the call for you. But the very next thing it prints is a distribution of the residuals. So, if you have watched the other videos within this little playlist, you'll note that there's one on the intuition of ordinary least squares regression, where we kind of built this relationship between cups of coffee. Ooh, coffee. Thank you. All right, cups of coffee and the number of hours that an economics student can actually study, fueled by coffee. And so we noticed that we simulated some data, and we drew a line of best fit through that data, and we said that individual observations may not be on that line. There may be some random error component for an individual that makes them not quite on that actual summarized relationship. Well, if we back out then that residual or that error term for every single observation, we can actually specify a distribution for it. And the distribution of that error is probably one of the most important pieces of linear regression analysis, because it's what we can't explain that is the most interesting. Additionally, it's what we can't explain that usually tells us if we've done something wrong in a linear regression framework. So I love seeing a distribution of the residuals. So this gives us both the minimum, it gives us the maximum, it gives us the median, and then of course the first quartile and the third quartile. So it kind of gives us a nice little even spread, if you will. In theory, if we've done a good job with our ordinary least squares regression, then this distribution of our error terms should be centered around 0. The median should be equal to 0, because we know that in a linear regression sense, the mean of our error will be 0. The first quartile and the third quartile in absolute value should be equal, and the minimum and the maximum in absolute value should be equal. Everything should be evenly distributed, evenly dispersed. And what do we see? In this case, we don't see even dispersion. It's close. We're not that far off. Negative 0.009, that's really still pretty close. It's not that far off. From 0, it still isn't 0, but I mean it's relatively close. If I bring back up the console a little bit, let's see, we call this first model. Let's do mean of first model $ residuals, and so we can actually see the residuals here. And what do we see? Ooh, yeah, we see a number really close to 0. So the fact that our median is not quite at 0 means, yeah, we have some degree of kind of skewness, and it looks like it's skewing it a little bit more into the negative region than in the positive region. Now, we'd have to do some more in-depth analysis to see if this median is statistically different from what we just now estimated as the mean of our residuals. But nevertheless, we see some kind of movement away from that, and that gets more dramatic as we compare the min with the max as well. So I would look at this and I would say we probably can do better. If this model is suited, or if this data is suited for a linear regression framework, we can probably do better. So the reason why I think it's important to look at these is because, as we're going to see, when we try to actually generate a table of formal results for our regression model, this portion of the analysis will not be present in it. In fact, the majority of actual published articles does not include a distribution of the residuals. And that's important because as an applied researcher, that tells me intuitively exactly what we're missing from our model. And so that, to me, this should be included, but it isn't often included in that. So as you're looking at your own work and your own material, you need to make sure you zero in on what's happening with the residuals. the distribution of your dependent variable, in this case the log of salary, it will define the distribution of your residuals. And so that's incredibly important. If your dependent variable is not normally distributed, then an OLS estimator may not be perfectly appropriate for you. But we'll get more into that later. Next, we see coefficients. And so these are actually the betas that we typed out in our econometric model. And the intercept is beta 0. And then we see some other things happening here. Now, we have to be careful here because we have some factor variables. The first one being rank. So each individual either is an assistant professor, they are an associate professor, or they are a full professor, denoted by the appropriate qualifiers within that variable information. Now, we can't include a variable for each of those three factors. If we do, then we perfectly explain all of the variation in our data. So R treats those factors as if for each one, they're a binary variable. So if you're an assistant professor, you have a value of 1, and if you're not, then you have a value of 0. Likewise, for an associate professor, it takes a value of 1. If it's an associate professor, it's 0 if it's either an assistant or a full professor. And for the rank of full professor, then it's either a 1 for full professor and 0 for everything else. We can't include all three of those columns of data within our linear regression calculation. If we do, like I said, we have what's referred to as perfect collinearity. We perfectly explain all of the variation and why, and as a result, we fall into what's referred to as the dummy variable trap. So R rightly treats these appropriately, and it automatically kicks one of them out. So it eliminates one of them. So notice here for the rank factor variable, we have 3 possible ranks. We only have 2 estimated coefficients for it. Likewise, for discipline, we had either discipline A or discipline B. It eliminates the first one, and we have an estimate for discipline B. Likewise, for gender, we had both female and male as our binary gender. Now we've eliminated male. So each of these coefficients, for the rank of associate professor, the rank of professor, the discipline, and the sex, these are all relative to the omitted group. So you would interpret these coefficients relative to that other group. So we would say that here in this case, the rank of associate professor has a positively higher average salary relative to assistant professors, which of course that makes sense. And then of course the rank of full professor, it has even larger salary bump that is higher than the average value of an assistant professor. We see the normal estimates for years since PhD and also years of service, because those are just integers, and so that's kind of what we would expect. So we see these point estimates, and these are exactly what we're wanting to estimate from our econometric model. Next, we see a standard error. Now, a standard error has an actual formal calculation attached to that. We're not going to get stuck in the weeds of actually dealing with the math for that. But the standard error tells us basically a confidence measure. How confident are we in our estimate? The larger this number is, the less confident we are from it. So it's kind of a measure of uncertainty, if you will. If it's a really small number, okay, we're relatively confident. Our uncertainty level is reduced, and so it's small. The t-value is a statistical test, often referred to as a t-test. Now, the t-test is a relatively simple calculation. It's our parameter estimate, so its corresponding value over here, minus our null hypothesis value for this. And in almost every statistics program I've ever seen, the default is always 0. The null hypothesis is always 0. So we're always measuring ourselves as, do we have anything? But the null hypothesis is that we have nothing. That's our initial starting point. There is no relationship. There's no important factor. We have nothing here. And then we see if we can provide evidence through the data to reject that null hypothesis, that hypothesis of nothing. So the t-value being the estimate minus our null hypothesized value, which is that beta is equal to 0, divided by our estimate of uncertainty, our standard error. So notice here, in terms of this calculation, since our hypothesized value is 0, the t-value calculated here is always the estimate minus the standard, or divided by the standard error. And if you actually manually take these calculations and take this number, divide it by this number, you'll get this number. If we're following a standard normal distribution for this, then the t-value at around a 95% confidence interval, it would be right at 2. It's 1.96. So you can loosely say for a t-value, if the absolute value is greater than 2, great, we have something there at the 5% level. Or we can look at the p-value. The p-value is the probability that the null hypothesis is true. I'll repeat that again. The p-value is the probability that the null hypothesis is true. So, if it's really, really small, then the probability that the null hypothesis is true is small. Thus, we would reject the null hypothesis in favor of the alternate, which is in that case in that one of these betas is not equal to 0. So we can see for our intercept, we have the p-value is less than 2e to the negative 16. Now this is just an error or a degree of precision problem here. 2e to the negative 16 is the default for when R stops calculating degrees of precision. It can keep going if you tell it to, but this is just kind of the default for it. And this default kind of means that, okay, at this point, we're relatively confident we don't need to go any further. You should be good with this. Any reasonable researcher would be good to go with this, and so we just kind of move on. Sometimes you'll see 2e to the negative 16, and then it just stops, and it doesn't really go beyond that. Can it? Sure. I mean, look down here in our console window. We have our estimate for our mean, e to the negative 18. So it certainly has the ability to go to higher degrees of precision. But it just, for statistical reporting purposes, it just doesn't. So here we can see a whole bunch of asterisks beside here. We see a period here, 1 asterisk here, 3 here, all along here. Usually if you see anything happening over here within R, you have something there. These kind of denote the degrees of cutoff for our statistical probability. The single dot is going to be at the 90%, the single asterisk is at the 95%, 2 asterisks is 99, and then 3 is 99.9. So here we can see right off the bat, a majority of these variables are important to explaining our dependent variable. Their estimated coefficient is statistically different from 0, so they're important. They should be in our econometric model. But it looks like that our gender qualifier for a binary gender is not statistically significant, at least on this first pass. All right. Also, you can have you don't have to remember all that about the what each of those things means. You have a nice little key code down here for the significance codes. Next, at the bottom, we see residual standard error. Residual standard error is basically the standard deviation of our residuals. So it's if we take the actual residuals that we're summarizing here and calculate the standard deviation of all of these, then we get this number. Now, this number is not necessarily important by itself. Usually we look at residual standard errors when we're comparing different models, and we generally would want the residual standard error that is smaller. So this is more of a model comparison calculation than anything else. On the next line, we see multiple R squared and adjusted R squared. And so we'll kind of explain the interpretation of those. They have a formal calculation behind each one of them. We're not going to get stuck into the math on that. But multiple R squared gives us the proportion of our dependent variable that our model can explain, or the proportion of our dependent variable that all of these factors jointly can explain. So we can see a number like this. It's bound between 0 and 1. So if we converted this into percent terms, then we would interpret this as 52.48% of our dependent variables variation can be explained by all of our independent variables together. Which generally, well, that's not too bad. We have to be careful with R-squared calculations, and I'll come back to that after I explain the adjusted R-squared. Adjusted R-squared, notice here in this case our adjusted R-squared is slightly smaller. Why is it adjusted? Well, in an intuitive way, we can keep throwing variables here. Now, we don't have any more variables to throw here. That's explicitly recorded within this data frame. But in theory, we could keep collecting data on these individuals and keep throwing information out there. And some of those variables might stick. Some of them might not be important. Some of them may be really, really important. But the more variables we throw in this model, the more we're going to explain. Adjusted R-squared has a penalty calculation. There's some additional terms in there that penalize the adjusted R-squared, or the multiple R-squared calculation, for including junk in our model that just doesn't belong in it. And so as a result, this reduces or tends to reduce multiple R-squared and kind of deflate it, if you will. It penalizes the researcher for just throwing everything up against the wall and seeing what sticks, if you will. Now, adjusted R-squared, we do see this kind of frequently. Multiple R-squared's got to be bound between 0 and 1. It's kind of a necessary feature of how it's calculated. Adjusted R-squared, because of the penalty calculation here, it sometimes is possible for you can get weird things. Sometimes you can see adjusted R-squared is greater than 1. Sometimes you can see them less than 0, in which case they kind of don't have that much meaning. If that happens to you as an applied researcher, look for something else. There's other kinds of statistics and calculations for determining model fit. Maybe focus more on residual standard error and kind of move on a little bit, if you will. But even if you needed something that kind of summarized the overall fit of the model, not compared to another model, there are other tools out there. Word of caution on relying too heavily on adjusted R-squared. I see this a lot, especially within fledgling researchers. We tend to say, oh, the higher these values, the better I'm doing. Yay, good. Well, yes and no. Usually when you start to get really high values, or values really, really close to 1, that usually points to me you're doing something wrong in terms of your model design. It's really easy to overfit our data and then possibly come up with what we would call a spurious argument, or a logical argument that it's not really there, but just kind of happens to be true for that one specific case. So we have to be rather careful with relying too heavily on adjusted R-squared. Finally, below that, we see our F statistic, and I love that R produces this F statistic. Not every statistical package does, but I think it's a really helpful feature within R. So the F statistic is basically a hypothesis test of, is your model crap? And it compares the model you've estimated against a hypothetical alternative model with absolutely no independent variables in it. All it has is an intercept, a constant. So this is really kind of just a nice applicable calculation of, do you have anything at all? Do these variables jointly, all of these, have any joint real effect together? Or are you just arbitrarily throwing something in here and it doesn't really matter? And I see this frequently. Statistical models thrown out here that you might think, hey, there's a reason to include this, but then when you actually put this data in, it has absolutely no effect. The F-stat, or the F-test, is a one-tailed test, so it's always going to be a positive number. It's not going to be a negative number. The further away from that point of origin, or the larger the test statistic is, in this case it's 71.79, the less likely the null hypothesis is to be true. So what is the null hypothesis? That the two models are the same. The model that you've put together as your researcher and the model with just an intercept. And so if they're statistically the same, then basically you've got nothing. This has both a numerator and a denominator degrees of freedom, so you'll see two different estimates of degrees of freedom. If you want, look more up on what an F-stat is. It's a ratio of two ratios, if you will. And then, of course, we have a p-value here. And that p-value is the probability that the null hypothesis is true, which is the null hypothesis that all of these betas are jointly equal to 0, that they're not important in our mathematical relationship. We have a very small p-value here, so we're happy to report, yes, we have something. Yay, we're good to go. Great. Right now our video is kind of getting long, so I'm going to stop here. I encourage you to kind of play along at home, so please dig in with the data, look back at the previous video. Like I said, the link will be in the comment section below, and start typing some of this stuff out and get familiar with it. Break it, get stuck, get an error message, and then figure out what's different between your code and the code here in the video. It's only with exercises like that we actually learn what we're doing. So great. I'll be back with another video shortly, and we'll kind of go to see what some of the other things that this linear model calculates. We'll look at some other diagnostic tools, and then we'll start to tweak it and possibly account for other things. Until then, I'll see you guys later.